Hello everyone, in today's video we'll be covering Enthalpy Changes 3, in essence, just bond energies. This is something that you're really familiar with in your IGCSE years, and it's the only thing that's covered from enthalpy changes in your IGCSE years. It's a very simple topic, but it can get confusing sometimes, so let's cover it today. So before everything, unlike in IGCSE, there's a proper definition of bond energy in your A-Level Chemistry or AS Chemistry. And the definition of bond energy is the energy required to break 1 mole of bond in gas phase. Okay, the two most important things in this definition are 1 mole of bond in gas phase. You see that whenever you're talking about bond energies, everything must be in gaseous phase. So like Cl, Cl, this bond must be broken between chlorine in gaseous phase, or Br, Br. It's the bond energy given when this bond is broken when they're in gaseous phase. I hope that makes sense. So that is the definition of bond energy. It can't come as a definition. I don't see it being tested otherwise. Anyway, let's continue on to the next part, which is the formula of calculating enthalpy change when bond energies are involved. So the formula is the enthalpy change is the sum of the the bonds being broken minus the sum of the bonds being formed. The bonds being broken are on the reactant side, so it is sum of the enthalpy change in the reactant side minus the sum of the enthalpy change in the product side where the bonds are being formed. So let's have an example. So let's say CH4 plus Cl2 forms CH3Cl plus HCl. This is a free radical substitution, an organic reaction that we'll be covering later. So in this case, the enthalpy change of this reaction would be given by, well, I'm not going to include R here because we already have an R and that denotes reactants. So the enthalpy change of this reaction would be the enthalpy change on the the reactant side first. So it'll be CH4, right? Plus between Cl minus the bond energy 3 times CH and once Cl plus HCl. Whenever you have calculations involving bond energies, I recommend you draw it out like in this form, so that every time you are including a number, you just cut it out. So let's say the bond energy of CH is 410, if I recall correctly. So for each time you include a 410 in your calculation, you just cut off each CH bond. So that means 4 times 410 in this case. I hope that makes sense. So let's do an example question, yeah, and then let's do a few example questions, maybe one or two, and then we can move on to the past paper questions, the type of questions you can expect to see in your past papers. So the first question I have for you is, well, okay, well, let's take the previous equation only. CH4 plus Cl2, right, gives CH3Cl plus HCl. Now, in your data booklet or in your papers, you'll be given a data booklet. Now, I think that changes like in 2021. No, not 2021. For 2022 onwards, the data will be given directly in your in the papers and the questions. But before 2022, all the data is provided in the SF16, I suppose, if I recall correctly. All the bond energy values are given in the SF16. So you can either resort to the SF16 for this question, or I just gave you the values. So CH is equal to, I think it's 410, not sure. 1 by 4. So yeah, no, the exact value in this case is 413. CL is 243. CCl is 346. and HCl is 432. You don't ever have to like worry about memorizing these values. It'll be given in your data booklet. Okay, so first try this. Anyway, let's proceed. So the enthalpy change of this reaction would be, wait, just remove that. The enthalpy change of this reaction would be uh, the enthalpy change on the reactant side minus the enthalpy change on the product side. For those of you who have done A2, this may be a bit confusing when you compare it to the entropy of a reaction or the entropy of a system, because in entropy of a system, it's the products minus reactants, but in enthalpy change of a reaction, it's reactants minus products. Sometimes people get it confused. They get it mixed up, but that's something you worry about later. So just for now, focus on this. So as I recommended earlier, draw this out. So CH times 4, right, plus Cl minus 3CH plus CCl plus HCl. Now, when you do that, so it's 4 times CH, so 4 times CH, 413, so that's 1652 plus CCl. When you cut CCl, that's 243 minus 3CH, so 3CH is 413 into 3, that's 1239, plus CCl is 346, plus HCl is 432. And so the answer is minus 122 kilojoules per mole. Yeah, and because it's negative, you have to include the sign always, and since it's negative, we know this reaction is exothermic. Not information that's required for this question, but I guess it's best to have all the information either ways. What's wrong with having more information, right? So that was one example question. Let's move on to another example question. Okay, CH4 plus 2Cl2 gives, no wait, sorry, yeah, CH4 plus 2Cl2 gives C plus 4HCl. Wait, HCl. Okay, what is the enthalpy change of this reaction? Oh wait, before that I have to provide the values. Sorry. CH is 413, Cl is 346. No, not 346. Wait, let me just get the value. Okay, sorry, it's 243. C alone is 700 something, 717, and HCl is 432. So calculate the enthalpy change of this reaction. Well, let's proceed. So the enthalpy change would be, well, I won't write the formula down because that's obvious, so I'll just start writing the values. So 4 times CH plus 2 times Cl, right, minus 717 plus 4 times HCl. So that's equal to 1652, right, plus 2 times ClCl, that's 486 minus 717 plus 4 times HCl. Why is that? Okay, 4 times HCl, and that is 1728. So your final value is minus 307 kilojoules per moles. Okay, this reaction also is exothermic. Now the types of questions that you can expect from bond energies is either calculating with types, right? So the types of questions that you can expect is either calculating the enthalpy change of a reaction or calculating the bond energy. So let's say they'll give you the enthalpy change, okay, and they'll ask you to find the bond energy between two atoms that's not given in your data booklet. So these are the types of questions that you can expect in your past papers. So let's move on to a few past paper examples as well. So these are the past paper examples I was able to find too. Well, regarding most of the enthalpy changes questions, they involve enthalpy change of formation. So you'll rarely see bond energy questions in your AS question papers. So let's get to it. So this is summer 18, so May June 18, paper 21. That's the first question, which is for 20 marks, out of which not much is from enthalpy changes. Some of it is. This is from equilibria, this is from something else, and this is from acid-base behavior. Okay, so let's just cover till where it's relevant. So it's relevant till here. After this is nothing to do with enthalpy changes. Okay, so the first part of this question, so the information provided is that sulfuric acid is manufactured by the contract process. So that is the formation of SO3, right? So one stage in the process of conversion of sulfur dioxide to dioxide is the presence of a heterogeneous catalyst, vanadium oxide, V2O5. Okay, and they've made it easier for you. They've drawn the displayed form, so you don't really have to go ahead and draw the displayed form for yourself to make it easier. So the first question is state the effect of a catalyst on a reaction. Explain how a catalyst causes this effect. So catalyst on a reaction, not on equilibrium, just the reaction. So you comment on the rate of reaction. So catalyst increases rate of reaction, which also means speeds the reaction up. Increase rate of reaction, not reactions, reaction, by lowering the activation energy, which is EA. This is done by providing an alternate pathway. Okay. Let's move on. State the meaning of the term heterogeneous as applied to catalyst. There's only 1 mark, so all you have to write is just state what heterogeneous means. So means it is in a different state or phase from the reactants. Okay. Now let's move on to what we're what's related to our lesson. So some bond energies are given, right? Use the data and the enthalpy change for the conversion of sulfur dioxide to sulfur trioxide to calculate the value for S double bond O bond energy and SO3. So remember I told you that there's 2 types of question, and this one we are calculating the value of S double bond O in SO3. It's already given for SO2, so this question is a bit confusing because sometimes the candidates don't read the question or they're in a hurry to read the question. So in this case, they'll also consider the S double bond O value in SO2 to be unknown and involve that as X in their calculations. That was a careless error that was made in this year for this question. So anyway, let's continue. To make things easier for myself, I'm just going to draw this down here, but I doubt you'll have to do it in your papers because you're doing it on 1 page, right? So you can just glance up and make all the cancellations there. Okay, gives 2SO3. And the enthalpy change is minus 196, I believe, right? Minus 196. Yeah. It's an exothermic reaction, so the enthalpy change is equal to the enthalpy change of reactants minus enthalpy change of products. So that would be twice 2 times, so 1, 2, like twice it gets cancelled out, and that twice times 2. So 2 into 2 will be 4, so 4 times 534, what's given here? So 4 times 534 is 4 times 534. I'll just write it as 4 times 534. 4 times 534 plus O2. So when O2 gets, that's 496, right? That's the reactant side minus 2 times 1, 2, 3, right? So 3, that times 2, that's 6, minus 6, and we don't know this S value, so it's X. We consider it as X. And that equals minus 196. So you make X the subject of the equation, right? So 6X is equal to 4 times 534 plus 496, right? That's 2632 plus 196. Therefore, x is plus 196 divided by 6. So x is 471 point. We'll just leave it at that because everything's given in 3 significant figures. So that's plus 471. It's important to include the signs in enthalpy change questions, but since it's a bond energy, it's obvious that energy is required to break it. So I don't believe it's necessary in this necessary to write it here, but it's better you do either ways. So the next question is also something that's pretty confusing. Majority of the candidates did not score full marks for this question. Yeah, so this part is independent of like what comes here. But anyway, let's just give it an attempt, just skim through it. Let's explain why boiling point of SiO2 is much higher than SiO3. Well, SiO2 is giant covalent, whereas SO3 is simple molecular, right? Uh, and then you compare the bond energy, like what needs to be broken and the strength of the energy required to break them. So for SO3, it would be at max permanent dipole to dipole, or just weak intermolecular forces relative to stronger extensive covalent bonding. So that's why it has a higher melting point. Amphoteric oxide. Amphoteric means it can behave as both an acid and a base, and then use chemical equations to illustrate your answer. So one equation of it acting as an acid, so which is with an AOH, a common one, and one equation acting as a base, so with HCl, easiest. And state what you would observe when a small sample of Na2O is placed in water. Well, that you have to write the equation out, and whatever you see is whatever you write. Okay, let's move on to what's relevant. So selenium selenium is a group 16, which is basically group 6, right? If you just ignore the transition elements, which shows similar chemical reactions to sulfur. Selenium reacts with fluorine to form SeF6 molecules. So SeF6 means 1, 2, right? 3, 4, 5, 6. So predict the shape of the molecule. So it's like this. So the shape would be octahedral. Anyway, let's move on to the next question. The reason why this was confusing was because his candidates did not know like what to consider, because there's just bonds given here that don't make sense, like in a normal equation. In a normal equation, you just have it as complete, but in this case, it's given in the polymer form or repeat unit form. So let's read the question. But when you read the question carefully, it actually completely gives away what you must and what you mustn't consider. So it says that the most stable oxide of selenium is SeO2. Okay, the gaseous SeO2 reacts to form solid polymer, which is shown like here. This is the solid polymer. Solid polymer. In this reaction, one Se double bond O is replaced by two. This is important. Let me just write that with red instead of blue, because that's what gives away by 2 SeO. That's what completely gives away what you must do in this, what you must consider in the calculation to form a polymer. The bond enthalpy for Se double bond O is 514. That's given. So use these data to calculate the bond enthalpy in kJ mole minus 1 of SeO2. So it's the second type of questions that I mentioned earlier. So enthalpy change would be enthalpy change of reactants minus enthalpy change of products, right? So enthalpy change of reactants is twice, so that's 2 times, so that's 514 times 2, that is 1028, right? 1028 minus, so 1 SeO, right? You cancel that out, so 1 SeO is 514 plus, so yeah, this is where things got confusing. So which bonds do you consider and which do you not consider? So some candidates, what they did was they only considered one SeO because that's the only thing that's shown, and it's the way that the equation is perfectly balanced. Some candidates instead, those who are a bit familiar with A2, they considered the bond here with O and the bond here with O. But for this case, you don't really have to consider both. The correct thing to do is just consider one of the bonds, only this one. The reason why I say that is because it says in the reaction 1 is replaced by 2 Se single bond O, right? So these are the only two things that you must consider. You don't consider this, you just ignore it, right? So if they said that this entire thing, like this repeat unit, if they ask you to consider the repeat unit, they wouldn't mention this, and the enthalpy change would be different. Okay, so in this case, you consider one here and one here. You break that, you break that. So there's two Se single bond O, right? So that's 2x, and that is your variable. X is SeO, right? So that's 2x, right? And that equals what? Minus 346. So when you make 2x the subject of the equation, so that's minus 346 minus 514, right? So that is minus 346 minus 514. That gives minus 860, right? So x therefore is equal to plus 430. Plus 430 kilojoules per mole. The rest of the equation, well, SeO shows similar reaction to SO2. Reaction with SeO2 with sodium hydroxide, it reacts as an acid because SO2 is an acidic gas, right? Okay, so that is it for bond energies and bond enthalpies. If you do have any doubts, please leave them in the comment section below, and if you understood, please leave a like, subscribe, and share with your friends.